This lecture is going to be over section 26.2. We're going to look at two-source interference of light. So when you have two light sources and they're coming in through, say, a couple of different slits, or maybe light from the same source, but they're coming in two different slits, you've got constructive interference occurring at a point where the difference in the path length from the two sources is 0, or an integral number of wavelengths. Destructive interference occurs when the path difference is a half integral number of wavelengths. So when the lines from the sources to a distant point P make an angle with a horizontal line in this figure, the condition for constructive interference is going to be that the d sine of theta, which is, it makes an angle here, and this angle, if you take whatever this distance d is, and you take the sine of that particular angle here, which happens to be the same angle here, d times the sine of that angle is going to give you the length here. So if you're if this is equal to some integral number times the wavelength or whatnot, that you end up with constructive interference. The condition for destructive interference is going to be when that is half of a wavelength apart. So if you look at one of the earliest quantitative experiments involving interference, you're going to go back to 1800 and you're going to look at some of the experiments done by Thomas Young, who was an English scientist. His experiment involved interference of light from two sources. Now, Young's apparatus is shown here in this picture. You've got monochromatic light coming through this slit right here, which, when they say that, it's about 1 micrometer or so wide. It falls on a screen that has two other narrow slits, and each of those are about the same distance wide, and they're about a few micrometers apart. Now, according to Huygens' principle, the cylindrical wave front spreads out from slit 0 and reaches these slits in phase because they travel equal distances. The waves emerge from slits S1 and S2 and are therefore always in phase. So this is considered to be coherent sources. But the waves from these do not necessarily arrive at point P in phase because of the path length differences. Pardon me. So you can see monochromatic light here. You can see the cylindrical wave fronts as they come through. You can see the coherent wave fronts from the two slits. And you see bright bands where the wave fronts are in phase and interfere constructively. And the dark bands are where the wave fronts are out of phase and interfere destructively. So this is the same figure that we saw before, where you have the two slits here. You've got the wavelengths coming, or the waves coming through here. They're striking on a screen here at some point P. They're going to have a difference in these path lengths defined as d times the sine of theta. Again, this angle and this angle are going to end up being the same measurement. So that's how we know that this angle here and this angle here are the same. If we take whatever the distance here is in the slit and we multiply it by the sine of theta, we can see that this difference here is what's going to trigger these bright spots and these dark spots on the screen. The actual geometry here is that we are treating the rays as parallel, in which case the path difference is simply this. We assume that the distance r from the slits to the screen is so large in comparison to the distance d that the slits, between the slits, that the lines from this are very nearly parallel. It's something along these lines. This is usually the case for experiments with light. So the difference in path lengths is going to be given by this. So we found in section 26.1 that the constructive interference or reinforcement occurs at point P, where the path length difference is here is an integral number of wavelengths. So again, you can see that the bright spots are going to be where this is true. The dark spots on the screen are going to be where this is true. And you can see the interference fringes produced by Young's double slit experiment. You can see here the bright spot here, 1, 2, 3, 4, 5, although you can see that it does begin to darken a little bit as you go further out. And then you can see the dark spots here when you're half a wavelength apart. So the positions of the bright fringes in Young's double slit experiment can be done with this particular measurement. If you know the distance r here, which you should in this particular experiment, then you can come up with this particular relationship. So you got a few problems here that you can work through, a few tutorials, and it will give you a good practice with this particular concept.